1 amp here, and I say, if I integrate all around this loop, what is that total integral of B dot ds? Integral of B dot ds around this whole loop. And the answer is, I add up the currents that are inside. If there's another one over here, like 7 amps, it doesn't even count at all. It doesn't go through. But here I have one that goes 2 amps up, 3 amps up, so that'd be 5, but you subtract the 1 amp going in the opposite direction, so the answer would be 4. So on this problem, the integral of B dot ds would be equal to 4 times mu naught. This will be the last of the modules or sections in Chapter 28 on magnetic field sources. Here we're going to address 28.6 and look at how Ampere's law was modified by Maxwell. And we'll end up with one of Maxwell's 4 equations. Well, to begin with, we have to recall what did we have for this Ampere's law. Well, Ampere's law stated that the integral of B dot ds, that's the integral around a curve that's closed, curve C that's closed, around any closed curve, is equal to mu naught times the current that's inside. So for example, if we have a wire and we take a circle around that wire and we integrate what B is, of course B is going to be pointed like this. If the current's going in this direction, B is going to be, by the right-hand rule, going around the wire like this, coming out of the paper at the top, going over the front, dabbing back under. And that will give us B. This is a very, very important equation. This is Ampere's law. But now we have a problem. This was really the incredible thing that Maxwell did. What if this wire right here dead ends in a capacitor plate? And there's another capacitor plate over here. And the current can continue here. You can say, well, how is it possible that current could flow here because it can't jump across the capacitor? Well, if I turn a voltage on back here between this point and I connect these two ends with a battery, then in fact what will happen is charge will begin to accumulate on this one and be pulled off of this one. So since the current flows this way, this will end up being positively charged and this one will be negatively charged. Now, what Maxwell thought of that was ingenious was the following. Let's imagine that this is very, very small and this loop is very, very large. If this loop is large, it says I count the current that's inside here. Well, that means there's a magnetic field here and here and here and here. But once I get to the part where there's a gap, it would say the magnetic field is 0. Because if I integrate around here, there's no current that flows in the middle. Believe it or not, this was a stroke of absolute genius worthy of a Nobel Prize. And what he did was he said, okay, I still have a magnetic field out here, but it's due to something else inside. What could it be due to? Well, if this is a capacitor, then we know that there's an electric field that's going to flow here between one plate and the other one. And we know that certain equations concerning the parallel plate capacitor. What would that be? Well, this is kind of a simplistic derivation, but here's what we can say. We can say, for this parallel plate capacitor, we know that the charge per unit area divided by epsilon naught is equal to the electric field. Now that's true inside a parallel plate capacitor where Q per unit area over epsilon naught gives us the electric field. So that'll be the electric field inside here. Now I want to solve that equation for Q, and that will give us Q is equal to epsilon naught E and to be times A. Well, if I think about it, this is, since this charge is constantly changing on the surface, I can look at dq dt, which would be epsilon naught d by dt of E times A, as though this is a type of current, a charge change per unit time, and add it to the one that's already here. So Maxwell suggested that we write the integral of B dot ds, which is going to give the magnetic field here, 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 all these different places, as, well, here it would come from mu naught I that's inside, plus mu naught times another kind of current. This is called the current due to Maxwell, the Maxwell current. And I'll write it here as epsilon naught d by dt of E times A. Well, rather than write simply E times the area of the capacitor, what we can write here is the integral of E dot d sigma over this area that's bounded by the same curve. So we have a curve here, we have a curve here, and we're going to integrate over any surface that's bounded by the curve, and that's an open surface, so we don't put that little circle here, E dot dA, and that will give us E times the area, and this is what Maxwell proposed as the correct equation, and this is the modified Ampere's equation due to Maxwell. And Maxwell collected all four of the equations and showed how those four equations would give the integral of B dot ds and the other equations, the two Gauss's laws, and another equation that we haven't had yet, and that those four were sufficient to determine the electric and the magnetic fields everywhere. Here's the proof. I kind of write it out here in the notes, but here it is in a little bit more detail that perhaps you can follow more easily. And of course, this is one of the real triumphs of theoretical physics in the late 1800s, about the time of the Civil War. Maxwell, who was a Scottish physicist, pulled all the equations on electricity and magnetism together and gave us these four equations. This is the third one, the Ampere's equation modified by Maxwell, right here. And so this one, plus Gauss's law for electricity and Gauss's law for magnetism, give us two more, and then there's a fourth one we'll see shortly.